This is Beth, a personified chess-playing robot that I built. Not only is she named after Beth Harmon, she plays just as well. In this video, I will walk you through her physical construction and how she functions. Beth is constructed similarly to a CNC machine. There is a wooden base with a handmade chessboard, and mounted on top is a gantry, enabling movement along the Y, X, and Z axes. The gantry is powered by 3 stepper motors and 1 servo motor. 2 steppers on the Y axis, 1 on the X, and a servo powering the Z axis. The Z-axis holds a small electromagnet that can be raised and lowered, as well as a stationary camera that faces towards the board. There are 3 calibration switches, and everything is wired to a Raspberry Pi and a stepper control board. Lastly are the custom chess pieces. You might think that these chess pieces look a bit odd, and you would be right. They are designed like this for 2 reasons. First, they must contain a metal washer so that the magnet can pick them up. And second, they need to have a fiducial on top so the camera can recognize them. Now let's talk about how she works. When Beth takes a turn, we need to capture the current state of the board. She moves her gantry to 2 positions and takes a photo at each spot. 2 photos are required because the camera is too close to the board to see everything, and a full fisheye lens would lead to some issues. The fiducials, which are these patterns, are placed on top of each chess piece in order to identify them. However, in the images, you will notice a problem. Sometimes, the top of the chess piece is located outside of the square that it's supposed to be in. This is due to perspective. You may have heard of perspective and orthographic before. You can think of perspective as the way that you see real objects. When you look at something, there are perspective lines that intersect with what you are looking at. As your position changes, so does the angle of the perspective lines. This changes how the object appears. Orthographic, on the other hand, is like something is infinitely far away, causing the perspective lines to become parallel. When you move, the object appears the same since the perspective is not changing. This is why faraway things sort of appear flat as you drive past them. We need to convert our perspective view into an orthographic view. Well, at least a representation of one. This way, the top of each piece will appear to be in the correct square. If we look at a raw photo from our camera, you'll notice that the lines in the image are not straight. This is because the camera has a wide-angle lens, which leads to something known as barrel distortion. However, we want our image to be rectilinear, which is when all the lines appear to be straight. We can correct for this by taking a bunch of photos of this chessboard-like pattern from a variety of different angles, and then we can run those through an algorithm that will spit out an image transformation. We can correct for the barrel distortion of any future image taken by our camera using this transformation. Here is our image before the correction, and here is it after. Now that we have a rectilinear image, we still have to deal with the perspective lines. Luckily, perspective lines are linear, so as the height of any point changes, its displacement from the center will change linearly. This may sound a bit complicated, but think of it like this. When you move a piece away from the center, the top and bottom move at the same speed, but from the camera's perspective, the top appears to move faster. We can actually approximate a coefficient for the difference between the top and bottom of each piece, allowing for us to correct the top position to match the bottom. I did this by taking 2 photos, one of the pieces sitting on the board, and then one where there is a fiducial at the base of each piece. I then determined the coefficient from this equation. We can then apply these coefficients to the top position of each chess piece to get an approximation of where its base is actually located. This essentially gives us an orthographic view of the board. As you can see, it's not exact, but it works well enough. We next need to figure out which square each of the pieces are sitting in. We know the locations of the pieces, as well as we know where the center of each square is. So we can pick the square that has the lowest Euclidean distance from a given piece. And voila! We have a digital representation of the current state of our chessboard. Now we have to decide what move to make, but first we need to verify that our opponent is not cheating. We know the previous state of the board and can extract the move that our opponent made to verify that it is legal. If it is, we run the Stockfish chess algorithm to determine our next move. Now, we make our move. The electromagnet moves to the desired piece, lowers down, magnetizes to grab hold of the piece, raises up, moves to the desired location, lowers down, and demagnetizes, releasing the piece. Beth is operated by a Raspberry Pi running a Python script. C++ programs are usually better for these kind of applications. However, Python offers great libraries for chess computation and image processing. For those operations, I am using Stockfish and RUGO respectively. The Raspberry Pi is connected to the cameras, stepper control board, sensors, electromagnet, and servo. Other than the Raspberry Pi, the only other board in use are 3 DRV8825 drivers that are used to power the motors. I won't be going into details about the code, but it is available on GitHub if you are interested in checking it out. Beth was a very fun robot to design and create. Watching her play is immensely satisfying, especially given that she has never lost while playing against a real person. Thanks for watching. See you next time.